Okay, so good morning, good evening, good afternoon, all, and thanks for joining us today. We've got a pretty packed schedule, so I'll keep moving through this. But today we're going to be looking at the role of demand flexibility in some of the emerging technologies that are coming out to start leveraging this and enabling the role of demand flexibility more widely in power systems. So if my screen will change, there we go. Today we're going to open up in a second with some remarks from colleague Vida Rosita from the 4E TCP EDNA to have some updates and to see what's happening in the world of the TCP and the exciting research and analysis that are happening over there. Then we'll have the first of our presentations today, which is on scaling up demand flexibility from peak management to efficient system operation. And that's one of the newest publications here at the International Energy Agency, where we look at the growing role of demand flexibility over the coming years and decades. Chris Matthew, International Energy Agency energy analyst, will be giving an overview on that report. Then we'll have a look at the role of plug-in battery storage systems for enabling flexibility from Rusty Langdon from the Institute for Sustainable Futures. Then we'll have demand flexibility protocols with interventions there from Anson Mu and Yang Vihan from Vihan Mugu. And then finally, we will have a look at the potential for flexibility within the data center sector. And that will be from Dr. Dirk Bouwknecht from the OCCO Institute. And then finally, I'll come back at the end to provide some closing remarks. To keep us all moving along nice and timely, please, Vida, the floor is yours. Have we lost Vida?
She's muted, I think. And
thanks, Dirk. And thanks, Brendan. It's a great pleasure to be here today and participate in this exciting event, which I know will be packed with lots of exciting insights, new ideas, and areas that policymakers can continue to delve into. The Efficient Demand Flexible Network Appliances Platform, which is part of the IA Technology Collaboration Program on Energy Efficient End-Use Equipment, brings together 12 national governments plus the European Commission, where we exchange ideas, we commission studies, we identify policy gaps, and we get the best consultants that we possibly can find, and you'll see a few of them here today, to make studies and to help us extract what are the insights that policymakers need, what are the areas for policy making to further look into, and how do we grapple this complex and continuously emerging area of demand flexibility. And we look at policy frameworks, flexibility potentials, technologies, and digitalization, and implementing flexibility. And what are we seeing on the ground, and what can we do to achieve the scale needed, which I know Chris will also be talking about today. And beyond this work stream, we also have a growing work stream on data center energy efficiency, with some exciting modeling work going on, as well as some further studies. And we also look at the efficiency of connected devices. And now, in terms of next steps, building on the portfolio of knowledge products to date, and I do encourage you to look at our website, where you can see hundreds of different studies over the past decade that could be of relevance still today. And we have new fresh studies coming along on almost a weekly basis. So building on this portfolio, we're in the process of developing a framework to further help us extract useful policy insights and to identify areas for future studies and work. So we look forward to working together with Brendan and colleagues and finding opportunities on how we can share these insights with you going forward. Thanks again. Back to you, Brendan.
Thank you very much for that. There's certainly so much activity going on over at EDA, Edna, at the moment, and has been in recent years, but you seem to have kicked into a new gear at the moment, and really excited to see what's coming up there in future. So now we're going to go over to our first major intervention then this morning from my colleague Chris Matthew on our newest report, Scaling Up Demand Flexibility. Now, this report we launched which seems like an era ago, but it was just 2 weeks ago at the 11th Global Conference on Energy Efficiency, which was held in Montreal in Canada this year. And this report was launched by our head of the Office of Energy Efficiency and Inclusive Transitions, Dr. Brian Motherway, together with an opening address from the Minister of Environment and Energy Security from Italy, Minister Pichetto Fratin. And before we go straight into this first presentation, again, just on behalf of the IEA, I'd like to recognise the support from the Italian Energy Ministry for supporting the 3DEN project. That's the Digital Demand Driven Electricity Networks initiative, which I've been supporting here at the IEA for the past 5 years. And have supported the IEA's research in power system modernization and digitalization. And this is one topic which is growing in more and more importance in this era, is as the demand side is becoming more diverse, more distributed, but it's also becoming more digitalized. We look at the role of digitalization for unlocking demand side flexibility. And Chris will be able to tell us a bit more about that now, as he gives us some overviews of the report and some of the key messages. So without further ado, Chris, please, the floor is yours.
Thanks, Brendan. So yeah, as you described, I'll just be giving a couple of insights from this recent report, which I just put in the chat if you're interested. And yeah, I'll just give you a quick summary. So to start with, kind of step back from demand flexibility and looking at the need for power systems flexibility and how we see this evolving in the coming years. So a major driver for this is integrating variable renewable energies. And so obviously renewables such as solar PV and wind are now some of the cheapest sources of electricity generation. Many countries are looking to dramatically increase how much of this provides their annual electricity demand. And so integrating these renewables comes with corresponding increases in the demand for system flexibility to manage the intermittency. And so what we see in these major world regions is this could grow by up to 7 times over the next 10 years. And kind of traditionally, this flexibility has been mainly provided by supply side resources, mainly thermal generation and hydropower, but increasingly we're seeing battery storage and demand flexibility as emerging and potentially lower cost options to also meet this growing flexibility demand. And so specifically for demand flexibility, there are kind of 2 main types that today peak shaving is kind of more widely used to manage demand at peak periods of the year. So this is kind of just the very few couple of hours of the year where demand is highest, tends to have an outsized impact on overall system costs. And so represents potential for cost savings to manage these periods and keep down overall costs. But then moving forward, kind of what we're seeing emerging in many places is moving towards load shifting, which can kind of feature on a more day-to-day optimization of the grid by managing shifting demand again away from these peak periods and increasing demand at lower price periods, particularly when there are large surpluses of renewable energy on the system. And so to take a quick snapshot of demand flexibility today, one of the the key case study countries we looked at in this recent report was South Africa, but this could be basically any country in the world. This kind of highlights the key point for why peak shaving is so important is that these few peak demand periods have an oversized impact on overall system cost. So for South Africa, just 10 hours of the year, 0.1% makes up nearly 3.5% of the total peak demand. And what this means is these peak periods are usually met by expensive peaking generation, which in South Africa is open cycle gas turbines. And these, so in South Africa for 2025, these made up around just 1.4% of the total annual energy demand for South Africa. But that 1.4% of the generation ended up costing around 14% of the total operational costs due to the kind of much more expensive fuel and lower efficiency of these generations. So managing these very small, say for South Africa, say 10 hours of the year, could have really outsized cost savings. And so this is kind of evidenced when we look at many major economies that in between 2023 and 2025, up to 9% of peak demand was managed under these peak shaving programs, depending on the country. And so again, these are kind of generally through kind of infrequently activated peak stress periods. So in countries where heating demand dominates, this might be in the winter, and for cooling, countries dominated by cooling in the summer. And generally, what we've seen is that due to the kind of technological limitations and kind of ease of communication, these peak shaving programs are generally provided through industrial users. Simply that industry tends to have some of the largest single energy demands, and so without without the network of interconnected technologies and automation of demand shifting, this means that the industry represents some of the best sources of peak shaving today in all these countries. And so moving forward towards this kind of more daily integration of peak shaving and a kind of more routine system optimization approach. What we see for Ireland, again, one of the case study countries in this report for looking from today through to 2035, what we see is that growing the potential for demand flexibility and through kind of load shifting, in addition to peak shaving, would require significant growth in smart technologies, and the kind of the scale of this expected growth can kind of be brought back to the sort of policy support for these technologies. So kind of for Ireland, the most mature of these you can see down the bottom is smart meters with just around 20% growth through to 2035 expected. And this is due to the kind of decades-long push that Ireland and the EU have had for deploying smart meters, which for Ireland, I think is currently over 80%, maybe approaching 90% coverage for consumers. Then and the kind of next level up in terms of the growth rates, there are technologies like smart thermostats and the industrial Internet of Things, which are expected to grow at kind of more modest rates without such supportive policy packages to encourage their deployment. We see these kind of being deployed by residential, industrial, or commercial consumers, given the potential for cost savings when combined with the dynamic or time of use tariffs to shift demand to periods of lower prices and away from higher price periods. And then lastly, the technologies which are kind of expected to have the greatest growth rates are those which form part of many countries' decarbonization plans. So things like heat pumps and EVs. These are things which are a key have a key role for decarbonization plans and electrification of end uses, and are starting from a kind of much lower base than smart meters today. So we expect that for things like smart chargers for EVs could see up to around a 10 times growth over the next 9 to 10 years. And so what do these technologies mean in terms of the potential for flexibility on the system by 2035, shown here for load shifting on the left and peak shaving on the right. So there's quite a lot of information in this graph, but I'd kind of just like to draw your attention to two kind of key points. That for load shifting, the kind of vast majority could be made up by electric vehicles and heating and cooling, which kind of really shows how this kind of interaction between the technology and how it's used and what role the energy service has, and how this kind of translates from the underlying demand into demand which could be flexible. And so particularly, I think EVs really stand out because in terms of the overall annual energy demand in Ireland, for the projections we've used in this model, EVs could have around 2.5 times less annual electricity demand than transportation, but at the same time, but transport also has the same amount, roughly the same amount of potentially flexible demand over the year. And this really shows how EVs technologically and I mean by virtue of consisting of a large battery storage unit have much greater potential to shift demand over the course of the day, which in turn contributes to a much greater share of potentially shiftable demand over the year. And then just the one other thing to note is that peak shaving, we anticipate through to 2035 would still be dominated by industry. And this is mainly due to the kind of greater price sensitivity of the industrial sector to variations in electricity prices. And so yeah, this kind of highlights how the preferences of consumers needs to be taken into account in making projections about flexibility and how the energy is used at a sort of basic level is a really important part of understanding how much of it could be flexible in the short and medium term. And so what does this demand flexibility potential mean for the system? So to understand this, we developed a power systems model of Ireland in 2035, which took the flexibility potential in the previous graph and included different scenarios of flexibility. And what we saw is how greater flexibility on the system allows for greater utilization of lower cost generation, particularly renewables, but also cheaper gas peaking generation, as you can see in the middle of the graph. And so what this does, kind of by shifting the curve over to the left, it has the effect of reducing the overall cost of the system. And what we see for the model setup in 2035 is a 10% reduction in in total energy costs over the course of the year. But I should say this is also offset by a slight increase in the in peaking gas generation, which is kind of caused by having these greater ramp rates over the course of the day, where the system has to adjust to accommodate flexibility coming ramping up or ramping down, and this results in the small increase in the red area you can see kind of on the left side of the graph. But this is obviously offset by the green area and these cost reductions. And so that kind of caveat leads nicely onto the next topic of highlighting some of the challenges around integrating greater shares of demand flexibility. So for the last case study country we looked at of Thailand in 2030, this issue is also highlighted looking at changes in line flows between. So the graph on the left shows line flows between modeled nodes in the region, in the country, and this kind of highlights how electricity flows on the transmission lines between around the country and what effect this demand flexibility could have. So we can see from the total peak demand that there's a clear reduction, which is definitely should be beneficial for in terms of the scale of network upgrades required and on the transmission system, but also distribution network. And this could allow more effective utilization of the existing network and lower the investment costs needed to meet growing electricity demand. But then, as the graph on the left shows, this benefit is not kind of uniformly distributed and really depends on the demand in the regions and where the flexibility is located and when it's activated. And so for kind of 3 out of the 5 regions, we see a general decrease in the flow between these between the modeled nodes, which would indicate that you could get this could encourage more electricity demand on the system for the same network capacity. But for one of them, the NEC on the fourth from the left, we see an increase in these flows, which would mean a lower use out of the same network. So this we see is kind of highlighting how managing this flexibility would require careful coordination between the transmission and distribution network operators to make sure that it's not adversely affecting outcomes anywhere in the system. And then just quickly on the back to South Africa on these distributional issues that we see for low-income households, around just 9% of their average daily demand could be shifted, whereas for high-income ones, this could be up to 50%. And so this is due to lower-income households having a higher share of non-shiftable demand like cooking and lighting, whereas high-income ones have higher shares of things like hot water and washing and drying, which are generally more able to be shifted in time. And so this kind of highlights, again, this is an issue that's fairly common for distributed energy resources, but kind of highlights how policies, if equity is deemed kind of part of an issue as wider policy packages, then this could be an issue that would need to be addressed by flexibility programs. And so just quickly to finish off, we see demand flexibility as kind of arising from this interaction of these kind of 4 main pillars of the end-use technologies, the digital infrastructure and the market arrangements, and the consumer participation. And so kind of making or getting to the point of say the flexibility potential in 2035 in Ireland, you saw a few slides ago. really requires all of these pillars to be in place um, to kind of make the best use of that resource and have it available on the grid for when, but also where it's needed. And so how countries can unlock this potential, a really key part is first understanding this resource and measuring it as part of system planning. Having this digital infrastructure that the last the last slide highlighted, and then also making sure that consumers can have a key role in participating, and that their expectations are kind of managed in developing programs. And this, yeah, again, kind of feeds into flexibility market design and making sure that consumers are kind of have a central role to this, but that it can also form an efficient part of day-to-day market operations. And yeah, this then can kind of feed into to integrating demand flexibility alongside other flexibility sources in the system and a more efficient power system in the future. And so with that, I will say thank you very much and pass it back to Brendan.
Thank you very much, Chris, for that brief overview. And just to remind colleagues who've joined us a few minutes into the session that the link to this newest report from the IEA, Scaling Up Demand Flexibility, is in the chat. And we'll share some more links as we go through the session of some other recent publications. And just to point out, that is a very brief overview of the report. It's a very comprehensive view and analysis on demand flexibility with over 600 data points within the report. So I encourage colleagues to seek that out and to read it in a bit more depth to fully understand the analysis. And what we've been doing is looking at the changing role of demand flexibility in recent years by looking at the kind of the new loads that are coming online, EVs, heat pumps, industry, data centers, etc. But another area which has seen huge growth is in the world of batteries and battery storage. Last year, 2025, the battery market accounted for around $150 billion. That's growing 20% year on year from 2024. And the role of batteries as energy storage is growing really at an exceptional pace, with the amount of batteries being used to store electricity when it's abundant during the daytime, primarily from solar, but from wind and from other areas, to balance the power systems has grown 20-fold in the last 5 years alone. And so to hear more about the role of plug-in battery storage systems, I'm now going to hand over to Rusty Langdon from the Institute of Sustainable Futures to give us a bit more information on that. So please, Rusty, the floor is yours.
Great, thank you. Just share my screen.
And that's perfect.
Hi, everyone. Yep, so my name's Rusty Langdon. I'm a senior research consultant at the Institute for Sustainable Futures at UTS in Sydney. And much of, hang on, I'll just change my view here. Yep. Much of my research is focused on batteries, and so today I'm going to talk to you about most recent research on plug-in battery energy storage systems. Very grateful for the funding for this research from the 4E EDNA group, and I'll refer to plug-in battery energy storage systems as plug-in batteries throughout the presentation. So if you hear me talk about plug-in batteries or plug-in BESS, it's all the same thing. So get into it. But firstly, I'd just like to start by acknowledging the traditional owners of the land I'm speaking from today and pay my respects to elders both past and present. I'll be speaking on 3 different topics relating to plug-in batteries. So first, I'll go through what they are, the different sort of system characteristics and technical capabilities. Then I'll talk about the benefits and limitations of these products for demand flexibility specifically. And then lastly, I'll finish with some information on the status of regulations and standards for plug-in batteries and point out some of the regulation and standards gaps. So first, what is a plug-in battery? So for the purposes of our research, we defined plug-in batteries as batteries that were a stationary energy storage system. They were designed for residential environments. They could be plugged into a standard residential power outlet. And they can be plugged in and operated by a non-technical person. And with that, we came up with 3 types of products that were sort of within the scope of the research that you can see here on the right. 2 of these products, the standalone plug-in battery systems and the plug-in batteries that would be associated with the solar system. We sort of defined them into 2 categories. So these batteries that are sort of sitting in this green dotted line can export electricity to the home circuit and or grid. And we also, through our research, came across portable power stations, which don't specifically feed electricity back into the grid, but they're increasingly being used for sort of off-grid backup, electricity backup, where appliances can be plugged in directly to them. So here's a bit of a table showing you some of the products that are available on the market right now. There's a lot of information here, so I'm just going to put on my little laser pointer and point out a couple of things. So plug-in batteries, they come in different system configurations, which means they have different capabilities. They can do different things. So the AC coupled systems here, you can see 4 products here on the left. They don't have connections for solar panels. They're designed to be standalone. And they could be used in addition to a plug-in solar system if it was already plugged in or plugged in separately. Or could be used with a hardwired solar system that was already installed on a roof, for example. But in that case, it would result in really reduced conversion efficiencies because the electricity is having to be converted multiple times between the solar to AC, back to the battery to DC, back to AC to use in the household. So you get some fairly big inefficiencies there. Hybrid systems feature solar panel connection points, so you can plug your solar directly into the battery system. They're more efficient than the AC coupled systems for the reasons that I just mentioned. Basically, you've got an inverter built into the system that allows that plug-in from the DC system and converts it automatically. So yeah, it's a bit more efficient. Now, both of these systems are similar in their demand response capability. They both have a bidirectional inverter that enables them to be charged from the grid and also send electricity back into the home circuit and or grid, depending on the limitations of the region that they're installed in. Some other key information that I'll just point out is that there's a default export limit that these batteries are set up to do. So this is 800 watts for most of the models. And this is based on export limits that have been set in different countries, different jurisdictions that have legalized plug-in systems in general. Some of the products do allow you to set within the apps a high export limit. So you can see that the product here can go all the way up to 2.5 kilowatts export. But to set that, you need a professional to check, the condition of the wiring in your home circuit and make sure the switchboard will handle injecting that much energy into your circuit so that you don't overload things. So it becomes a little bit less plug and play in that situation. Individual battery capacity starts at just under 2 kilowatt hours, but you can stack these systems, sometimes through connected cables, sometimes the systems plug directly into each other and stack on top. And you can see the EcoFlow system here can stack up to 23 kilowatt hours in total storage capacity. Next slide. And so here's a few more products available on the market. The left two batteries are DC coupled systems. So the inverter is separate to the battery up here. You can see the two inverters here. It allows solar panels to be connected, but they're connected to the inverter directly. And then some DC coupled systems only have a unidirectional microinverter. So like the big blue product here on the left, it limits the ability to do that demand response, the range of demand response, because you essentially can't charge the battery from the grid. It's directly from the solar. So it's fairly limited what you can do there. And then on the right, there's just a couple of examples of the portable power stations that we collected some information on. But again, only suitable for off-grid use. They don't have any grid export capability. So now I'll jump into some of the wider benefits and limitations of plug-in batteries for demand flexibility. And there's a few reasons why consumers are choosing plug-in batteries over hardwired solutions. They're simple to install, there's minimal electrical work in most cases, faster setup. There's reports of them being available, in the UK in the future from a local hardware store, and you could plug it in yourself and be running in a couple of minutes. So there's great potential there for rapid uptake of this technology. Of course, you do have the limitation of the 800 watt total export. So if you want to be able to sort of export higher than that, you might need the involvement of an electrician to be able to set up your home electrical to do that. They're portable, they're relocatable, so the battery can move house with you if you move a lot or if you're renting. So in terms of that period of the return on investment for the batteries, which tend to be a bit longer than solar systems, you can see out that return on investment if you sell your property and you've got a hardwired solution. That system stays with that house, and you might not see that return on investment. The lower upfront cost. So typical system prices range from about 750 euros up to 2,000 euros and average about 400 euros per kilowatt hour. A hardwired residential batteries average about 700 euros roughly per kilowatt hour. And in looking at some of the forums and the groups on Facebook, people have reported that it's great that they're modular and scalable, so you can start with one and sort of add to the capacity as you need it. So that's sort of a benefit there. Potentially faster deployment than hardwired batteries for all of the reasons that I've just mentioned. The plug-in options create a new opportunity for renters and people who live in units to access clean energy options. So where previously they've been locked out of that. So it's a real energy equity issue, an opportunity to level out that playing field. And then plug in batteries as virtual power plants. The potential is there. The storage capacity might be small individually, but if you install a million batteries over at 2 kilowatt hours, that's a decent amount of storage capacity. So the demand flexibility benefit is real. So this slide is just showing the products that these plug-in batteries integrate with for smart home energy management and demand response. Some smart meters. Not all the plug-in batteries require this. You can plug in a battery and just manually set an export limit. But that would result in some grid export if your home isn't using the same amount of energy. So if you set it at 800 watts and your home's only using 200 watts, you're exporting the rest of that to the grid essentially. So, but in a smart solution, everything's sort of automated for you. So some of the regions have zero export limit, so you do need a smart meter to manage so that you're not exporting to the grid. So a couple of examples, we've got the sort of wired smart meter on the left here that uses CT clamps to monitor energy flows, but a little bit more complicated to install, would need an electrician or, someone very competent with electrical to install one of these. And there's this P1 smart meter that you can plug into the P1 port up here on your electricity meter, but not all regions have the P1 port, as far as I know. So this is an option in some areas, maybe not others. But basically, the P1 meter integrates with things like smart sockets to monitor energy demand from individual appliances. But these smart meters integrate with the plug-in battery apps, and you can connect to these smart meters and basically control when you're using energy and use certain settings. I'll just show you the energy management apps, some examples here. So both of these example products, in both of these examples, the energy management app enables price response, so you can set your plan or tariff structure in these apps. Some of the apps actually have the electricity plans already sort of in the app, and you can kind of select it. Or if your retail plan's not there, you can kind of put in the details manually. Can do load shifting, so you can use your solar during the evening peak, or peak shaving with a smart meter, so you can reduce your load on the grid during times of peak energy use. And I guess this is probably where, unless you're stacking a huge amount of battery capacity with a plug-in battery, this is probably more what plug-in batteries will play a role in, the peak shaving, just reducing that little bit of peak. Oops. Am I still sharing?
And we see the presenter's screen or the main screen of the slides.
Oh, sorry. There we go. I think I just accidentally clicked something. So,
No, that's good now.
yeah, good. Okay, so the limitations, obviously, there's total capacity limitations. So, yeah, that 800-watt capacity again. Once you start to go over this, you're introducing the need for sort of an electrician to get involved, to make sure the circuitry is safe. Yeah, again, some countries restricting that. The export limit requiring zero export. And I guess there's a question on, how the smaller storage capacity compares with hardwired solutions. How many batteries can realistically be stacked on a balcony, for example? How many batteries are consumers likely to invest in before they consider hardwired solutions? And so I'll just finish now on the status of regulations and standards and sort of where things are sitting now in terms of adoption and support for adoption. So this table just gives an overview of sort of what's happening around the world. On the left, there's a lot of progress on plug-in solar legalization and standards around plug-in solar. Plug-in batteries, on the other hand, the only place that really has legalized plug-in batteries is Belgium. And they've got, a standard and like a certification standard that the batteries have to be tested to, or specifically the inverters have to be tested to. I've put in the US here because they've recently legalized plug-in solar. And they've got an associated standard, a testing standard for certification purposes, and they do mention in their battery storage, but it's only up to 1 kWh of storage capacity. So that pretty much cuts out most of the products on the market, I would say. But the structure is there, the framework is there. There's the potential for legalization of batteries within that legal framework and standardization framework. And then Germany, obviously the biggest uptake of plug-in solar systems and adoption of plug-in batteries as well. No specific mention of plug-in batteries in legal and standards frameworks, but there is going to be a new plug-in battery standard released. Yeah, I'm not sure when it's going to be released, but it's been noted that they're working on that. So I won't go into detail here. There's a lot of detail in the report on standards and regulation and what's needed and what's out there, and all of the details that, like, the key points in that. So can go through the report, have a look at that. I'll just highlight a couple of some of the gaps that sort of I looked at, and we did some stakeholder engagement during the research, and some of the stakeholders noted, particularly with cloud-based smart integration, there was a highlighting of some of that cybersecurity risk associated with cloud-connected devices, and particularly with batteries, given that you wouldn't want someone to, a bad actor to potentially control that device and set it into thermal runaway or something like that. And in terms of product updates and support, the plug-in batteries sitting in more of that kind of consumer product category. will they be supported, for software updates and for a long enough period to make sure that they're safe, performing appropriately for their intended life. Not unique to plug-in batteries is standardized requirements for product performance data and information. This is across all batteries. There's just really inconsistent information on product data sheets, on product websites, documentation, around performance information, particularly efficiency performance. There's inconsistent information on the product capabilities and functionalities, missing information, and inconsistent information on the consumers related to emergency fire response. And there's a regulation gap around portable power stations. And it looks like consumers using those portable power stations indoors and potentially not understanding the risks there. So, and that leads me to, a fairly significant gap on where should the plug-in batteries be allowed to be installed. So we highlighted this in the report. There's fairly strict guidelines on where hardwired batteries can be installed, but no specific requirements on where they shouldn't be installed for plug-in batteries. And then there's some product manufacturers are recommending that could be installed in habitable rooms like bedrooms, kitchens, lounge rooms, and etc. So some work to do there on creating some standards and frameworks around what recommendations, best practices, and standards around installation if it's a DIY install. And that's it from me. So thank you.
Thank you very much, Rusty, for that comprehensive overview of a lot of different technologies, a lot of diverse technologies out there as well, and how they're starting to integrate the various platforms as well. And behind that, then, I suppose, is a lovely segue to the next section, where we have intervention from colleagues Anson and Jan, who'll discuss some of the protocols that sit behind that. In a lot of the conversations we have with various stakeholders here at the IEA, interoperability comes up every single time when we're talking about digitalization, be that from the technology provider, the governments, or some of the research institutions which we work closely with as well. So looking forward to hearing a bit more information on the protocols and how that fits into the world of demand flexibility. So please, Anson and Jan, the floor is yours.
Thank you, Brendan. And also thank you, Vida, for inviting us for this webinar, where we will be presenting the study that we have carried out for Aetna on demand flexibility protocols. On this slide, you can also see the front page of the report. Vida has put the link to the report in the chat. So, Anson, please, next slide. Very brief introduction to the study. So the purpose was to recommend a realistic global pathway for adoption of application layer specific application layer communication protocols. And the work method was that we had did some literature reviews of existing work, and we made an amount of interviews with the market players and did some assessments. And we had also some dialogue with the Aetna members. The team, I was product manager, and Anson, that will be presenting the following slides with the technical content. He was the senior expert in the team. And then we had connected to junior experts, Sarah and Matthias. And we did the work, well, we started June last year, and we are finishing after this webinar, but most of the work was carried out in the second half of 25. So Anson, you please take the floor and present the rest of the slides. Thanks.
Thank you, Jan. My name's Anson, as Jan's already introduced me. I know we're running a bit over time, so I'll try and keep some of these quite short. This is really just to say that, in fact, our study was looking at appliances, so water heaters, HVAC, pool pumps. We weren't focused on PV and batteries, which obviously have different functionality, the ability to store energy, the ability to supply energy into the grid. And because we are looking at appliances, as Chris already explained, we are looking mostly at the ability to load shift. And by doing so, we're able to preserve the service to the user, to the consumer, which is quite critical. To do this, I think the general consensus is that you use some sort of price signal in the most case, or perhaps even a carbon signal if you want to increase the amount of renewables. And what we haven't looked at in much detail, and I'll explain later, is the role of sort of explicit controls. So the price signals, we tend to refer them as implicit flexibility. But in terms of explicit flexibility, the sort of load shedding that you might need to do in an emergency situation, or even sort of planned ahead load shedding, is not something we focused on. And also because this isn't where your gains are made. You're wasting renewable generation in that case, or you're perhaps affecting the service to the user. So this is a diagram just to try and explain, because what we are thinking about when we talk about interoperability, if I just... Sorry, just skip the slide there. I'll just try and get the laser pointer up. So if we imagine, for the most part, we start at the grid, who sends a signal about what sort of action or what sort of thing they need to happen. The grid might go to some sort of aggregator, and this signal, there'll be some protocol that's needed, and there's an interface between them. The aggregator would then send a signal perhaps to a home energy management system. Again, there is a protocol and interface, perhaps a different one, and therefore there's some sort of translation going on. And then finally, that the HEMS would be sending it to some sort of appliance about what to do. So, for example, start your water heating earlier, 2 hours earlier, before the peak rates. So when we think about interoperability, we've got multiple layers, multiple interfaces, we've got multiple protocols perhaps occurring. And also here, what's also very important is where the decision is made. So the grid sends a signal to say the price would be high at 7 p.m. And then the appliance then decides, in this situation where you have a direct signal, the decision would lie with the appliance. The appliance would decide based on the consumer preferences or what they've already set in an app or something, what the best response is in that situation. If you then imagine some sort of aggregator in the middle, the aggregator would normally make this decision, and in which case there'll be two translations that occur, but also it may be less optimal for the consumer because the aggregator is obviously trying to maximize its interests, and may not be able to take into account everything the consumer is looking for. So we have additional coordination issues and perhaps a less optimal outcome to the consumer. And then finally, again, this is the explicit route where the grid may say, we have some sort of issue, we're going to have too much demand, you need to shut down or drop down your heat pump power, almost immediately or something like that. And this is something, again, it's important, but it's not what we're looking at because it's really not. It's about the protection of the grid rather than enabling savings or improving the grid. And at the bottom we have just again the explanation of the additional layers and the additional complexities. So when we try and understand what is affecting interoperability and why it hasn't happened, there are actually a few different angles to look at: the technical, the structural, and also the timing issues. I think most people look at the technical and they see it as many different standards. So we have OpenADR and we have Matter or something, and then we have many manufacturer proprietary protocols. And they see it as just, if we pick one, this would solve it. But in fact, we can have one protocol, but different manufacturers or different appliances might implement different parts of that protocol. So the protocol might have bits for different appliances or just sort of slightly different ways of saying things, like any sort of language. And if you don't understand every single part of that protocol, or so, there's some sort of vocabulary you're missing, it might just get ignored. The next layer down is you get the instruction, you understand what the instruction is, but how you respond to that might also differ between different appliances and between different manufacturers, so on. So you could have and it might not be even on purpose, it might be just some sort of software issue or just some sort of mistake in there, where the device is responding in some sort of unexpected way, and therefore you're not getting the savings, and then some adverse impacts to the grid may occur. And sort of highly related to that is the issue of testing and certification, especially for more complex protocols and protocols across different countries. What we find and the experience, for example, in Australia for the solar, was that the protocol wasn't developed as well as it could perhaps have been, and there was a lot of geographic fragmentation even between states in Australia, where they needed certification between states because they were all being implemented in slightly different ways. On the structural side, this is really about what's happening now in different places, and also different policy frameworks. So we're seeing that there have been different approaches. The UK is working on the grid signals through OpenADR. California is very much neutral on the protocol. And then we see sort of in Germany, the focus is very much on sort of the curtailment, the load shedding in emergency situations, similar to the solar in Australia. And then because of this, there has been a huge amount of investment. There's already a lot of existing appliances or meeting these requirements. So trying to unwind these investments, it probably is not a realistic thing to consider. And finally, at the moment, there is no sort of policy. There's no organization where policymakers can discuss this and try and work through the interoperability of issues at a geographical level. This mostly happens via the existing standards bodies who manage these protocols. Timing is another issue. We see different protocols come out. We see different revisions and protocols evolving. So trying to say we will stick to this protocol forever is probably not a realistic thing to say. And therefore, what you ask for must take into account the state of the art and the state of the market in terms of what the state of the art is and what the market provides, and not the same very often. And ensuring that you're focused on the correct problems. So for this sub-study and for what we believe, it's very much on this sort of demand flexibility and load shifting, rather than sort of the previous problems about curtailments of load and which more and more can be solved by batteries. So in this sort of situation, there's no interoperability. Manufacturers are taking a sort of a wait and see approach. They're also seeing where they are in different countries. They're having to have national teams to try and correct all these interoperability issues for each protocol and to certify their products. So this would obviously multiply in terms of cost greatly if every region starts picking different protocols. So what we propose is to have a framework so that we can really be clear about what we're discussing. What are we trying to agree interoperable protocols around? And so if you think about it in terms of the time horizon, so do you want real time or do you want sort of forward planning of hours and days? And what sort of signal? Do you want a direct signal to, curtail or some sort of market signal? We're really focused on this sort of forward planning, implicit flexibility, which is where load shifting occurs. So we really don't look at this area, the explicit flexibility. As we say, there's already things in place there. We're not going to be able to change it. And being pragmatic, this is something that each grid can manage themselves. This does mean we won't get perfect interoperability, but I think again, it's a pragmatic approach to getting interoperability where it's most important. So this is trying to place the main protocols on them. It's very hard because every protocol nowadays does almost every single part of this, but their focus tends to be in different areas, and that's what I've tried to show. So OpenADR is very much on this sort of market signal forward planning, but it can do service and indeed direct requests, whereas Matter has always traditionally been very much direct commands, switch on your light bulb, switch off a light or something like that. But it's quite simple things, but has grown and evolved and is supporting OpenADR. OpenADR 3, I should be clear. We are talking about 3 rather than version 2, or indeed 3.1. And then eBus is sort of somewhere in the middle. It's more around the service requests, but again, it's not to say it can't do the other areas. So based on sort of this framework and where we see the issues, we have a pathway to try and move us towards interoperability. We're not suggesting a single protocol, but trying to find the one that best fits the needs agreed by the regions and the policymakers. So firstly, having this shared vocabulary, having this framework lets us be clear on what we're trying to achieve, because if your focus is explicit flexibility, then perhaps this isn't something that we should be discussing. And this is the policy focus in a lot of areas still. And then with this agreement that we're looking at implicit flexibility, we suggest that we start at the market signals end. We're not looking at the direct commands for each appliance, because every appliance has its own commands, has its own ways of achieving sort of implicit flexibility. And if we do every appliance, we increase the complexity greatly. A market signal, just a tariff or something, is universal across all appliances. So this is also an important thing to be able to agree on. And the benefit of a simpler signal, simpler protocol, is that it's easier to implement and there are less chances of having compatibility problems, and the certification is easier or perhaps even not necessary if you can get it down to that level. Once we sort of agree on these signals, we want to try and agree how the device should function when it receives these signals, so that we have certainty about what happens when we say, the tariff is high, the heat pump won't switch on for some unknown reason or for some strange sort of strange logic. And this is sort of the next step in protocols, and you see that happening in some organizations, which we'll come into. And then, beyond having them function the same way is some sort of testing or certification, and a universal certification. So, a certificate issued in France would be accepted in the US or something like that, so that you're not required to certify across every region. And this would test that the device is functioning as expected based on the signals received, and that they understand all the signals that they can be expected to listen to. And finally, a general alignment on operability, interoperability based on all these areas. So another big question that we got was, what is the role of the home energy management system? It's seen as in some ways as essential and very much a benefit in that it can translate between different protocols from upstream. So, for example, some sort of OpenADR3 signal protocol. It can optimize across all your appliances. So it knows the situation between all your appliances. It knows the consumer needs, and it also knows there's a context. So it knows if you're generating a lot of PV or the state of your battery when this tariff increases. So rather than, tell your heater to preheat, it might just say, we can run off the battery for that period instead. And this sort of local context is lost when you tend to go up different layers. However, it's not, and I think what we missed here is also some reliability and stability. For example, if the internet went down, the HEMS would be able to keep managing the home. But at the same time, it's not a perfect solution. So, example, if you're like me, when the internet goes down, it's not the internet, it's my router. And if your router goes down, your HEMS goes down with it. So there are things to consider when you look at these things, and it's not a universal solution. Another thing to consider is the use of cloud-based HEMS. So particularly for the manufacturers offer these things, as well as the large Google and other large internet providers. And especially in the short term, where we're trying to maximize the amount of appliances available for flexibility, allowing this sort of cloud-based HEMS where they can deploy it rapidly, especially when things that might be not quite so mature and therefore need to be updated more often, and scale is something that should be considered, and it's quite a pragmatic way of operating. But there is certainly a role for HEMS in terms of translating between protocols and this optimization. And then the final sort of question we were asked was what is EDNA's role in this? How could they support this move towards interoperability? And clearly, the obvious role is this is as a platform to convene people, to communicate what's happening to everyone, and give them a forum to discuss what's happening, rather than the current situation where the regional coordination is within the standards bodies, where we have a individual organization like such as the Mercury Consortium working on these sort of device class functions and device specific responses to market signals. And within that sort of coordination role, they can help publish information, help develop some of these profiles, as well as publish updates on the latest events. So yeah, in short, it's a neutral convener and a catalyst to bring all the stakeholders together. Okay, and that's the last one. Thank you.
Thank you very much, Anson, for that overview on what ultimately is a very complex arrangement that currently exists. A lot of different actors in a lot of different areas using a lot of different languages to communicate with a lot of different products, and looking to see how we can move forward to have a more pragmatic approach to interoperability. It's a really interesting perspective, and great to see the EDNA's work in this area continuing to push the conversation forward with more research and analysis to fully provide that more of a granular approach to that the data to exactly what is needed to step forward. And one of the areas which was discussed, although it was in passing, was about how energy management systems could be using the internet to communicate, or the role of cloud-based providers to support some of those activities. But this is also a growth area of electricity demand for cloud services and digitalization, which is growing year on year. After a couple of I suppose years, even a decade of moderate growth up until around 2022. Since then, we've seen a real spike in demand for digital services and the emerging role of AI for increasing that digital demand. Last year, the total demand for electricity for data centers grew 17% in 1 year. And is expected to continue more as more and more of our economies become digitalized. So is this an area then which potentially could offer more flexibility to the system? Is an emerging area of research. And our next speaker, Dr. Dirk Buiknecht from the Occo Institute, will be telling us a bit more about what the potential could be here. So please, Dirk, the floor is yours.
Okay, thank you. Thanks for organizing this. There's not that much time left, but I'll do my best. You should be able to see the slides now, I guess.
Yes, that's all good. And please, you can run 5 minutes over. That's no problem.
Okay. Okay, wonderful. So we've done this study on data centers and flexibility, so a very specific user of electricity, certainly a very interesting one. It's growing very rapidly. It's becoming more and more important, and it's not like many of the other users that we've heard about, electric vehicles, heat pumps. They are directly connected to this idea of having growing renewables, which increase the need for flexibility, like the wind turbines here in the back. So we have this transition to renewables that requires more flexibility, but data centers is different. It's not one of these, okay, we need to use renewables, but the growth is for other reasons. And the growth is certainly significant. So we've done this study for EDNA at the Occo Institute based in Germany with my colleagues mentioned here. And when I talk about growing demand, just to mention one figure, so data centers worldwide will roughly double their electricity consumption between 2025 and 2030. And obviously, the more demand you have, the more flexibility you can also provide in principle. And we try to kind of disentangle the various flexibility sources here. In principles, you have the servers, as you can see here in the table on the left. You have the servers, the IT infrastructure itself. You have the kind of cooling that is relevant, and you have other supporting infrastructure. What is important is that the actual server IT infrastructure will grow. The share of that will grow because of better cooling efficiencies, as you can also see in the graph in the top right corner. We've looked at different types of data centers: enterprise, co-location, hyperscalers, and AI and high-performance computing data centers. So they have a different role to play. They have different flexibility potentials. they can then actually exploit. And obviously, the hyperscalers and AI data centers are the ones that are really growing and that will have the main share in the future. In order to better understand what kind of flexibilities these data centers can provide, we've looked at different flexibility functions that are needed in power systems, and that's something that actually applies also to the other demand side options and indeed flexibility options in general. So there is market serving flexibility. So this is really balancing supply and demand. This is basically what happens on the power market, on the power exchange. Then there's grid serving flexibility, which is about managing grid bottlenecks. And finally, there's system serving flexibility, which is used by the system operator, which is about maintaining stable power system operation in real time. These are the main functions why we need flexibility and what we need flexibility for in power systems. They have different requirement levels. The first one is kind of, if you like, the easiest one. You can trade flexibility in the market. The second one is more strict one, where grid operators typically have high reliability requirements for managing grid bottlenecks, to also managing voltage in their grids, increasingly also in the distribution grid level. And the third one, the system serving flexibility demand, is the one with the highest reliability requirement, where you really need to be sure that a contracted flexibility option is then available when you need it. So it needs to be on standby and needs to have short-term availability. So 3 different functions, 3 different reliability requirements. As I said, that's relevant for all the flexibility options and demand side options we've heard about. We've already heard in the previous presentation about different ways to address that, either via price signals, which obviously then have a lower reliability because you don't know to what extent people will react on these price signals, or you have more direct control options for the grid operator to actually kind of switch on the flexibility. What is also important to understand how data centers, or again, flexibility, demand side flexibility in general, can actually do to provide these flexibilities, is what is actually their exposure to this flexibility demand. So we need someone to fulfill these functions, but what is the exposure of data centers, in our case, to this demand? In the case of market serving flexibility, it's very high if you have dynamic tariffs, for example. So the data center is actually exposed to varying prices in the market. If the data center doesn't see these varying prices, then there is no incentive to actually provide that flexibility. And it's the same for grid serving flexibility. If you have flat network tariffs, as we have for many large consumers in many countries, then there is no reason whatsoever to react to any grid bottlenecks. So you need to have an exposure to that demand in the market on the operational side. And what is highlighted here in bold, and I think that's very important, especially for data centers, is the connection side. So it's not just about the data center is already in place and you operate it and you have some signals from the grid to react in a flexible way. But you need to have that flexibility to connect in the first place. And that's increasingly important because in many places we see increasing grid bottlenecks due to all the developments that we've heard about, increasing renewable generation, increasing electrification, and the expansion of the grid in many cases cannot really catch up with these developments. So we have increasing grid bottlenecks and therefore also increasing problems for new consumers to get connected to the grid. And flexibility is an option here. If you can provide flexibility as a new consumer, this can be a way to get a faster connection. And that can be particularly relevant for data centers. But again, this only works if there's a mechanism in place to actually kind of prioritize new consumers and data centers with flexibility. But if that's an incentive for flexibility on the connection side, this can then also be an incentive to use that flexibility once the operation has started. So we have different flexibility functions with different characteristics, and for all of them, you need to have mechanisms in place to actually exploit that. As for data centers now, more specifically, in the report, we discuss various strategies, and there are three main strategies. We've looked at workload flexibility. So that includes server power scaling, which is a bit like me now talking faster, but kind of conveying the same content, hopefully. You have spatial load shifting and temporal load shifting. So spatial load shifting is kind of shifting between different data centers in different locations. And temporal load shifting is kind of the temporal load shifting we've heard about before in the previous presentations. So that's kind of the core infrastructure, the IT infrastructure, the servers that can operate it in a flexible way. The second strategy is to use the supporting infrastructure. That's kind of all the cooling infrastructure, the infrastructure for uninterruptible power supply. It's backup generators, maybe on-site generators that can be used often, gas turbines. And the third one is to build additional assets to increase the overall flexibility of the data centers, for example, in order to get easier connections to the grid, as I mentioned on the previous slide. And these different strategies can be used for different flexibility functions that I have explained. The first one is most suited for market serving, which is kind of, as I've explained, the easiest one, where you can just trade flexibility that you have, but if you don't have it, you don't trade it. But kind of shifting the server operation around for the other two functions is certainly more difficult. Utilizing support infrastructure, in principle, could be used for all functions, but we are in doubt that it's actually then in practice useful for market serving, because this is something you don't want to use all the time. So market serving is kind of trading around the year, whereas grid and system serving flexibility is more used for specific cases, kind of emergency situations. And this is kind of what this utilizing supporting infrastructure is built for. For example, many of these fossil-fired backup generators, they also have emission limits, so you don't want to use that throughout the year, but you have just a limited number of hours. So that's why we think that's most suited for grid and system serving flexibility and additional assets. Basically, you can build what you need, and this can then serve all functions. But for all of these strategies, we have also identified barriers. That's relatively detailed in the report, so have a look at it. Just to highlight two of them, or maybe three. Service level agreements is an issue. So technically you could do certain things. You could shift, for example, workload, but due to the service level agreements that you have with your customers as a data center operator, or that you have in a co-location data center between the co-location operator and the kind of the customers in the co-location data center. So these service level agreements often restrict how much of this technically available flexibility potential you can actually use. And what is certainly also a key issue for data centers is opportunity costs. That's, I would say, an issue for all demand side flexibility, because you always have a flexibility option that was built, that was set up to do something else, to provide mobility, to provide heat, and you are playing around with it, and you always have an opportunity cost. But this is particularly relevant, we would argue, for data centers, because there you have potentially very high revenues, high profits, and kind of using flexibility to make a bit of extra money on the power market against these high revenues and profits is then potentially less attractive. And for the additional assets, obviously the key issue is that you have to build them. You have to invest first. You're not using what you have in place already, but you need to have additional investments. And taking all of this together, we've provided this overview, again, that's derived in much more detail in the report on the different data center types that I have mentioned, and these different strategies that I have explained. And building additional assets in principle has a high potential for all of them. But as I've said, you need to build additional stuff here at the bottom. What you can also see that utilizing the supporting infrastructure is mainly attractive in the case of co-location, and moderately attractive for co-location and hyperscale data centers, whereas the AI data centers often don't have a lot of additional supporting infrastructure. So there is not that much to use, and the same also goes for the enterprise data centers. So they are not so attractive in that respect. And for the first one at the top, enabling workload flexibility, you have the highest potential for hyperscalers and low potential, relatively low potential for the enterprise, whereas the other two are in the middle. You can see some of the reasons here explained, but if you want to look at that in detail, have a look at the report where we explain the different barriers differentiated by these flexibility functions and the data center types. Now, as a last point, we've also looked at some policy options. That was not the focus of the report, but is obviously also important. That's a summary table that we have in the report that looks at different policy areas that can be addressed and how this relates to these different functions. Just to highlight a few points, we would generally argue, so 3 main insights here, we would generally argue that in order to exploit demand-side flexibility and also data center flexibility, you need to have some kind of price signal, very generally speaking, which you get in liberalized and competitive electricity markets. So that is a very powerful tool to exploit, especially demand-side flexibility. But that's not enough, but you need to have specific governance mechanisms in place to remove barriers for flexibility, where we haven't found any specific data center barriers, but there are certainly barriers for demand-side flexibility. And you need to have certain mechanisms in place to provide, that's what I call exposure. So you need to have dynamic tariffs. You need to have dynamic network tariffs. On the connection side that I mentioned, you need to have flexible connection agreements. Otherwise, it's a nice idea, but there's no incentive for data centers to provide it. So this is kind of this design of liberalized markets. Then the second point is mechanisms where individual consumers need to procure or incentivized to procure electricity from renewables. If you do that in a way that they don't just buy an annual amount of renewables, but need to buy renewables or from renewable sources in a kind of disaggregated way, so hour by hour, as it is currently discussed within the Greenhouse Gas Protocol review, then that's a clear incentive for having flexibility, because this enables you to buy electricity from renewables in a disaggregated way, not just that much per year. And the third point, as the last point, is that we see certainly potential to also think about product policy instruments that already play an important role in kind of facilitating increasing efficiency of data centers, which is also a key topic of EDNA. So having certain minimum requirements, standards, voluntary codes of conduct, eco-labeling, public procurement. So there are lots of different instruments here that are also already used for efficiency of data centers. And this is something that can also be expanded to enable flexibility of data centers. But there we see an open task of what kind of indicators, key performance indicators should actually be developed to kind of measure that flexibility of data centers in an appropriate way. And that's it from my side. Thank you very much.
Thank you very much, Dirk. And it's a very fitting way to end the session today with policy recommendations. It's very much in the IEA format and template. So thank you very much. So, I mean, really interesting as well, just to finish off there, just to say that it's not just the ability to provide flexibility. It's everything else beyond that. It's the regulations, it's the policy considerations, it's the markets, it's the technology, and it's how all of this integrates together will determine whether we unlock as much of this flexibility that is possible to provide those services and system benefits that are there. So again, just to provide a quick overview from where we were today, at the top, thanks very much to Vida Rosita for providing us an overview of the current activities for EDNA and some of the upcoming areas of analysis. We then had an intervention from my colleague, Chris Matthew, who provided updates from the IEA on our most recent analysis, scaling up demand flexibility, and which included some modeling and analysis of the changing role of demand flexibility now 2030 and 2035 through a case study approach. We then had a look at the emerging role of some of these more interoperable plug-in battery systems from Rusty, and some of the challenges for integrating those in a broader way. And then we had a look at the protocols that underline all of this, the interoperability from Anson and Jan. And then finally, look at the role of the growth of digitalization, increasing loads from data centers, and their potential to provide flexible services. Although, as Dirk is pointing out, this is very much an emerging area of research, and there are many unanswered questions, market consideration, policy considerations, system security considerations going forward. So thanks to all the colleagues for joining today to participate, and also thanks to the colleagues who joined online. I can see there's a lot of activity in the chat. Really good to see that. And yes, for all the colleagues that have asked, we will be sharing a recording of this session, and it will be going up on the event page, and we will be sharing that with all of the registered participants in due course. So thank you very much again today, and look forward to the continued collaboration between the IEA and the 4E TCP and EDNA in particular. So that's all left to do. Bye-bye now.